Hello, everyone. It's an honor to be able to present the Semantic Analyser as a keynote in IMDIS. IMDIS is very close to my heart as a conference. And today I'm presenting on behalf of my colleagues Gwenaelle Moncoiffe, David Habgood, Enrico Boldrini, and Nicolas Carr. So I'll start with how the Semantic Analyser was conceived, and it was conceived during the FAIRIES project, which is a multidisciplinary project that aims to provide tools and services to scientists and researchers in order to be able to discover, access, and analyze multidisciplinary data in a collaborative way. The project is focusing on scientific areas of the Earth's environmental dynamics, the environmental biogeochemistry, and the biodiversity observations. Our role in this project was to provide semantic brokerage. And semantic brokers are really intermediaries that provide semantic translation services across diverse sources. And this is a list of the diverse sources that we had to deal with. And a lot of the sources we didn't know. It was outside of our comfort zone, so outside of the marine domain. And we had to provide semantic brokerage, which looks something like this. An example of that is that when a metadata record or a data set contains the term satellite, and another one, Sentinel, the semantic broker needs to establish that these are both names for a type of an observation platform. Next, we have to understand that Sentinel is a particular type of an Earth observation satellite, and then create the relationship between the two and make it available in a machine-readable way. So we really very quickly realized that we have diversity in our sources, and the diversity is in the language that is spoken by the sources, the technical language, and that looked like the Babel Tower. And the diversity is both in syntax and semantics, because the language consists of both of them, syntax and semantics. Syntax, in technical terms, refers to the structure of the format of the data, and involves the rules that define the arrangement of symbols, words, or elements. An example is that some of these research infrastructures use the OpenAPI standard for their web services, or the catalog services standard, or NetCDF to format their data, or XML to serialize metadata, or the ISO 19115, and many, many more. On the semantic side, semantics refer to the meaning of the data. So you see a symbol, and through its context, you know what it means. For us, the Sentinel and satellite is one of the examples that we encountered. Because I'm Greek, I just wanted to refer to where semantics come from. So it comes from the word semeno, which means in Greek. And semantics comes from the word semantikos, which is significant. So thankfully, the syntactic harmonization was taken care and was implemented by DAB, which is the Discovery and Access Broker, that was configured especially for the FAIRIES project. And these are the different standards on the left, my left, that the DAB, the Discovery and Access Broker, had to harmonize, and it provided all of them to us under a common syntax, which was the ISO 19115. So we are already harmonizing everything on the syntactic level, and now our job is to provide the semantic brokerage. And to provide semantic brokerage on that level, you need to really obtain a comprehensive understanding of the data sets, both on the metadata elements that they consist of, and then the values that these metadata elements get, which are the semantic artifacts. I'm going to be using semantic artifacts as a term to refer to controlled vocabularies that are authoritative list of terms, taxonomies, which are controlled vocabularies with hierarchies, thesauri, which are kind of taxonomies with a structure of, with relationships between them, and ontologies that are kind of taxonomies, but they have a lot of more relationships between them. So in order to be able to provide something practical and meaningful, we focused on 4 different metadata elements: the keywords, the parameters that are provided in a dataset, which are the variable measured, the instruments, which are the sensing or sampling instruments, and the platforms, which are the observation platforms. And we started analyzing manually initially. And we were faced with documents, XML documents like this, with strings as words that we needed to understand. Where do these strings come from? Are these coming from a controlled vocabulary? And then we started going to search portals for semantic artifacts to actually understand that, yes, there is a matching with this soil degradation. It comes from a vocabulary called ENVO, and then there is also phosphorus that may or may not come from that vocabulary. But we also encountered combination of metadata fields and labels that, again, were difficult to be found if you Google them. But then, again, we knew that this comes from the vocabularies that we manage in the NERC vocabulary server. So we started making some understanding for the semantic artifacts that are being used. Thankfully, we also had this case where the terms were annotated with unique URIs and labels, and that is actually how we would love everybody to be using vocabularies to annotate their data sets. And that took us to the result that actually our structured metadata that are really well structured are machine readable, but unfortunately they are not machine actionable yet because they need the human in the middle. The human in the middle to take all this information that is hidden in their minds and put them explicitly out into the machines to be able to make them machine actionable. And then we created the Semantic Analyser to actually do what we did manually, do it in an automated way. So the Semantic Analyser is a tool to analyze the semantics of metadata and data files across multiple domains. And as we said, initially it was created for internal use, but it can be used by external users as well. This is how the architecture looks like, and the analyzer is fed with metadata records and data files from the DAB, but with individual files that comply with the ISO 19115 standard or data files that comply with NetCDF. When they are received by the Semantic Analyser extracts terms from the structure of the XML or from the NetCDF, and it tries to match them with terms that are in the knowledge base. I'll talk about the knowledge base in the next slide. So the knowledge base has a lot of terminologies that we thought are and we were told that are relevant to the data sets that we were studying. The results are being presented in a tabular format to the users, and when terms have not been matched to anything, we give the users a chance to use federated search across different search portals like the Earth portal and the Bio portal in order to be presented with more matches. The knowledge base is an indexed triple store that uses the Resource Description Framework, RDF, as its standard. It has lots of controlled vocabularies, ontologies, and as we said, semantic artifacts that are listed here. And the number of them is also shown in this graph. So it's quite NVS heavy, the NERC vocabulary. It has 58 vocabularies from the NERC vocabulary server, but it also has a lot of vocabularies from the Global Change Master Directory, the European Information and Observation Network, and the French Cluster for Atmospheric Data and Services, AERIS. It has a lot of them because a lot of the metadata records were annotated with them. And we also assign a type in its vocabulary, not only one or more, so every vocabulary can be of type instrument, parameter, platform, or more of them. So semantic artifacts were also needed to be updated in our knowledge base because they are dynamic in nature, they are alive, more of them are created as new use cases emerge, and we had to find the frequency of updates. So for the NERC vocabulary server, we established daily updates, while for the rest of the knowledge base, we established a twice-a-year update, while still questioning what the optimal frequency of updates is. So this is how the Semantic Analyser looks like, and here the user can select a research infrastructure. Then users can select one or more datasets from the research infrastructure to be analyzed. Here, users can see the dataset, and they can see its XML as well. And then when you analyze your datasets, then you are presented with the basic metadata elements, the instrument, the variable, the parameter, and the platform, and the different methods that are used to do the matchings. So every term is matched against the knowledge base. First, if we find URIs and they match exactly, we show them up. If we find a term that exactly matches the knowledge base, we bring it up. And then if we don't find anything, we use the proximity match, and that brings quite good results. And then wildcard match is really a poor proximity match, but it still brings quite good results for things that have not been found. There is the case where terms have not been found at all, and this is where we employ the federated search to external search portals. This is how the analyzer looks like when it matches, it creates a lot of matches. So in this case, we had quite a lot of matches, and it presents them with showing what is the term that was searched, what it matched with, what is the category of the vocabulary it matched, and the method that was used. And this is how it looks when terms are not found and the federated search is employed. And after all this semantic analysis, we came with some high-level results of that analysis. And for the instruments, we found out that not many metadata records, so not many research infrastructures populate metadata records for instruments. We didn't find many exact matches, but we found many occurrences of not applicable and unknown. Wherever we found matches, they were coming from 3 different sources. One was the experimental factor ontology, the NERC vocabulary server with several controlled vocabularies, and the GCMD instruments vocabulary. Then on the platforms, the analysis was pretty much the same as instruments, not really well filled in. A lot of hits were matching satellite and ships. Many occurrences, of course, of not applicable and unknown. And then most of the matches were coming from the NERC vocabulary server and the 3 vocabularies shown up here, and the GCMD platforms vocabulary. On the parameters, the situation was different. So most of the research infrastructures fill in the parameters, and the usage of URIs was very much increased. This is the list of vocabularies used by the NERC vocabulary server, but they also used WORMS, which is the World Register of Marine Species, the GCMD parameters vocabulary, the NCBI, This is the Thea Oscar Thesaurus, which is for the critical zone sciences, and the Aeris, which is again from the French cluster for atmospheric data and services. What we learned is that it is important to use unique URIs and preferred labels to reference semantic artifacts in the annotations you provide on your metadata records and datasets. That interoperability of widely used semantic artifacts was a very good thing to notice, that a lot of semantic repositories use standards like SCOS, OWL, and RDF. That made our life easier, but it also highlighted something that I think most of us here know, that adhering to the standards does not necessarily achieve interoperability, because small variations can actually create very many differences that are not, cannot talk with each other. We found that there were many fair semantic repositories, but there are several that are not fair because they are provided as PDF lists or HTML pages on the web, and this hinders interoperability. And just another note to keep in mind that fairness is important because it enables machines to action, and we have to take all this knowledge that is in our minds and get it out on the machines. This is just a slide to provide knowledge on how to refer to semantic artifacts. This is for XML and this is for JSON. So be as explicit as possible using the URI and the preferred label. And this is where we are going next. So for the Semantic Analyzer, we want to enhance the knowledge base with additional semantic resources. Using feedback from the Semantic Analyzer, we want to improve the search methods, enhance the user experience, and we are currently working with the Blue Cloud project to provide useful reports and recommendations to the Blue Cloud infrastructures, and increase the fairness of the I, which is the I2, which is metadata use vocabularies that follow the FAIR principles and reference them uniquely. Thank you.